antennas, they have the ability to detect and process signal coming from different directions. However, the phased array antenna, they have one drawback. That is, they have the complex structure, and the cost for the processor, amplifier, or phase shifter somehow costly. And it is obviously that most of the previous antenna design is directed to the narrowband. So the wideband phased array antenna can be promising and need to be explored. There are one state-of-the-art method proposed by M.Hoang in his paper about the wideband phased array antenna synthesis. In his paper, there are some beauties like the side lobe can be minimized outside of the main lobe region. In the picture above, you can see that outside of main lobe, the side lobe will be minimized in a defined and fixed bandwidth. In the second picture below, we can see M.Hoang proposed and introduced a suppression region. In this suppression region, the array factor does not vary with the frequency. So it means that each sample in this region, they will decide the direction of the arrival signals. With the feature bandwidth now, I do not put it in advantages or disadvantages, because sometimes it's good, but sometimes I need a possible larger bandwidth. And M.Hoang method have one drawback, that is the side lobe cannot be arbitrary, because sometimes I want to suppress the side lobe in a specific direction. For example, the theta phi 50 degree or something else. So I propose a new strategy to overcome this drawback. Also, have the ability to obtain the possible larger bandwidth in the neutral feature. And my problem can be stated as define a set of the unknown array parameters that can satisfy the requirements and the constraint. With the requirement here, I have to generate a subbeam with high gain field onto the broadside direction, and also maximize the operational bandwidth of the given array. In the M.Hoang, he just gives a fixed bandwidth. Now I want to find maximum bandwidth. And in the M.Hoang method, he just minimizes the side lobe level up outside of the main lobe region. But now I want to put a user-defined mask on the side lobe level. We can define it in our way. Here, fixed element position, this is constant value because this is the given array. They give us the information about this. And the excitation here, this is the degree of freedom, and my main objective to obtain after using the synthesized method. This is alpha, delta alpha comprised of alpha 0 to alpha capital I minus 1. This is comprised of n variable. It depends on the array I use. For example, if I use the arrays of 10 by 10 elements, I will have 100 variables need to optimize after this time method. And here I fix the phase becomes 0 for efficient computation. Now I want to mapping from my statement to the mathematical formulation. For the first two requirements, the equivalent to the array factor at the specific direction equal to 1. Because in a normalized pattern, the array factor, the logarithm of 1 becomes 0, and this is the maximum form, and the side lobe or the mass constraint will be less than 0. For the upper bound, I put the user-defined constraint. It means that the beam pattern will be less than, so the array square minus the user-defined mass will be less than 0. This is my mathematical formulation. And the common weight among all frequencies here, because I have many frequencies, and each frequency will generate a different excitation, different set of factor alpha that I mentioned previously in the previous slide. So now I force the condition in order to obtain a unique excitation can generate different beam in the wideband. For the fixed element position, this is constant value. This information that the given array gives us. But But the question here is, how can we solve the constraint? Now, we take a look deeply to constraint. They have three sets of constraints. The first set of constraints is the array factor in 1. This is a linear constraint because we can see that array factor, this is the linear combination of the unos. In the formulation here, we can see that the array factor will be a summation of the unos with the cosine. The cosine function that contains of the specific direction, frequencies, and the position. The position is fixed. The specific direction we already know. The frequency in the bandwidth of the maximum or minimum we already know. So the first set is linear constraint in this time is the compressed set, and the meaning I already mentioned in previous slide. That is to have the some beam with the highest field along the broadside direction as a specific direction like theta 0 and p0. And the second set also a constraint because the square of the array factor minus the user defined, they have the form of the positive semi-definite quadratic form, so this is the compressed constraint. And the meaning of this constraint, I already mentioned, it's just in order to satisfy the user defined mask, it means that the beam pattern has to be below the mask. And the last set, I combine all the frequencies in order to obtain the unit isolation for all frequencies in the band of the minimum and maximum frequencies. Here we can see that I already proved that all omega 1, omega 2, and omega 3 they are convex. So the intersection of them is still convex. So my problem can be solved by convex programming problem. The next is my result. In my result, I tested for two square array with the different size, with the different mass, the symmetric mass and the anti-symmetric mass. The anti-symmetric mass means that I put a notch in the symmetric mass at the arbitrary direction. Here, the design constraint, the left above picture is the reference geometry comprised of 100 elements. Along the x and y axis, the inter-element spacing that equal to the equispaced with the 0.5 lambda 0. And the two right above pictures about the constraint. The constraint here is the user-defined max. You can define any, but in my case, I define is the outside of the square region. I impose minus 30 dB. And the extreme right picture, this is the cut on the horizontal axis of the middle picture. And the result is the left below picture. It is the distribution of the excitation vector alpha that I mentioned in the previous slide. The vector alpha now is comprised of 100 variables because the array is 10 by 10. And for clearer assessment or see the result, we go to the graphical presentation of two-dimensional beam pattern looking from top view. Here we can see the three picture above. This is range from the minimum frequencies to the maximum frequencies, and the three picture in the middle. This is the three cut of the 2D pattern from 0, 45, and 90 cut on the phi on the theta. With the different color, the red represent for the horizontal cut, the green represent for the diagonal cut, and the blue represent for 90 cut. And on the x-axis of the three picture in the middle, it represents for the theta value. The theta can be from minus 90 degree to the 90 degree, and the y-axis represents for the normalized pattern. You can see that the optimized pattern after using the compressed programming problem, they are below the mask that I impose on the visible regions of beam pattern, and it also satisfies the bandwidth from 1.35 f0 to 1.67 f0 with a threshold bandwidth 0.27, with 27%. the fractional bandwidth to rep. This is the information let us know about how large of the bandwidth. If it's greater than 0.2, it means that this is the wideband. And the next test on the array of 20 by 20 with the number of elements greater than now increased to 400. In the previous case, only 100. The constraints are the same, and the result you can see that this is the distribution. The highest in the original, and they gradually decrease in the edge of the array. The left below picture. And the same, we see that when we increase the number of elements, the fractional bandwidth increased from 27 to 87. The bandwidth now is ultra wideband. And the beam pattern now satisfies mass constraint. We see they are below. Here that I already mentioned. The fractional bandwidth increase when we increase the number of elements, but the trade-off here is when we increase the number of elements, the execution time also increase with more than 22 times in the case of 10 by 10, from 5 minutes to 3.5 hours. And the next time is just I put a notch in the mass at the direction of theta from minus 35 degree to 50 degree. You see that the left and width 10 degree and 50. I put a notch in this place and test whether the optimal beam pattern satisfies the constraint or not. And actually it satisfies. Here we can see that I put the notch in the horizontal axis, and so I just plot the red one. We see the red one in three picture in video. Therefore, at the notch, the optimal beam pattern they are lower than minus 50 dB. And the similar case for 20 by 20, only the number of elements increase. And however, the notch now I put is minus 50 dB. Here they are also satisfied. You can see at the position of the notch, the optimal beam pattern they are lower than notch for or the frequency in the band, and the fractional beam will also increase from 40% to 68%. Here my conclusion, what I have done in my thesis is I have to define a set of excitation that generate a beam with in a wideband that satisfies the constraint that is the user defined, not fixed. That is user defined. You can choose any mass constraint that you want. And the convex programming enable the efficient array antenna, array designs. Thank you for listening.
Thank you.
Yeah, maybe one question. So at a given point in your presentation, you thought that you are maximizing the operational bandwidth.
Yes.
Right? But in the equations, I didn't see such kind of effects. So my question is, are you maximizing the operational bandwidth, or are you increasing, let's say, the operational bandwidth without a guarantee to obtain the maximum of the bandwidth?
The maximum operational bandwidth.
You are maximizing it. So, but how can you guarantee to maximize the bandwidth?
Yes. In next slide we will mention about this. Because in the antenna properties, when a maximum inter element spacing greater than a certain wavelength, the grating lobe will appear, and it will violate our mass constraint. And by that point, I will obviously find the maximum frequencies. And from that maximum frequencies, I replicate the constraint by step. I replicate the constraint of the maximum frequency and the constraint of the next lower frequencies. If the convex programming base method return me as valid solution, I continue replicating the constraint of the next lower until the convex programming base method return me invalid solution.
It seemed to me that F-min and F-max were fixed a priori, right?
No.
They are not fixed a priori.
Yeah, it's not fixed.
So they are free.
Yes, we have to find.
Okay.
We have to find it by, I have to reduce the F0 to 60 GHz. This is the initial guess. I just show randomly. I just show 30 or 60, and then it return me a bandwidth. I do not set at the beginning.
So you don't set anything about the...
Yes, if you give me a given array, I just take the random F0, like 10 GHz or 60, I mean the initial case can be arbitrary, and then it's return me a bandwidth that satisfies my requirements.
Okay. And does it mean that this allows you to achieve a given bandwidth, a given desired bandwidth without any constraint, or there is in any case some constraint to be considered?
The constraint here is the mask, is the defined mask.
Okay, thanks.
Thank you for the comment. And the last one is about the computational complexity. So at the hand that when we double the number of elements, your, let me say, the CPU time grow quite. And first, what is your feeling about the load of increasing of the time for doing computation? Is of the order of the number of unknowns, or is twice, or is a log of the number of unknowns? First one. And the second one is that you have implemented this, okay, this is the solution is unique by definition since the complex program. But the point is that you have some limitation in number of elements you can deal with your code, or is arbitrary. I mean, I can put also 100 by 100 in our implementation now.
You mean the variables?
The number of variables, now we are using 10 by 10, the dimension of the array, 20 by 20. Do you have any upper bound in terms of the number of elements you can use now in your implementation? I mean, the complex programming code works for an arbitrary number, or there is an upper bound?
Because now the limit of the computer,
Yeah.
the machine, because I have to take the samples. For example, for 10 by 10 array, I have tried with the 2,000 samples.
Okay.
It's good. 5,000 is also good, so I chose 2,000. They generate the same result, but for the 20 by 20, if I chose 5,000 and 10,000, they are different. So I think that 10,000 is much better because we increase the number of the nodes. But however, now in the case, I mean that when I do with the higher element, I replicate constraint. So for example, 10,000. If I replicate for many frequencies, it means discrete time the bandwidth. For example, for bandwidth, I have to have 40,000 constraint. But now the computer, when we eat more than 100,000 constraint, the computer does not work.
But it's a round problem, is it for a CPU problem,
Yeah.
a round problem, or implementation of the code? I mean, the matrix is
Only the machine problem.
only the machine.
Yeah.
Okay. Thank you. Thank you so much.